At this time, I'd like to introduce Richard Steenbergen, who will be presenting everything you always wanted to know about optical. Richard is the founder and CEO of Petabit Scale, and this is actually his 34th time presenting at NANOG. Richard's first time speaking at NANOG was on a panel discussing XSP security vulnerabilities at NANOG 34 in Seattle, 2005. Welcome back to NANOG, Richard. We are certainly happy to have you back with us today.
Thank you. All right, so welcome to my tutorial, everything you always wanted to know about optical, otherwise known as Richard talks for 2 hours and everyone tries not to fall asleep. So the purpose of this tutorial, and this is one that I've given many times and it continues to be very popular because it's really addressing something that is not well understood in the internet community. Lots of us here run routers, plug into fiber, and we don't really understand the details of what's happening, why it's happening, what are the economics, what are the technology factors that are driving that. And why we do what we do with it. So the purpose of this talk is really to kind of introduce everyone to that space and make sure that we walk through every kind of major component that's involved in working with optical. So it's not going to make you a optical expert. There's a whole lot of math in here that I'm leaving out, but it really, the point is to make everyone informed about all of the major issues. So you kind of understand what you're working with when you're doing it. So start with the very basics of fiber optic transmission. So ultimately, what is fiber? Why do we use it? What's the big deal? Well, really, fiber is a waveguide for light. So you put light in one end and it comes out the other end, and it's usually made of glass, some silica of some form. It can also be made of plastic, but big reasons to use fiber. It's very low cost. You can make very cheap, very long, very high count, thousands and thousands of strands of fiber in a very small cable. It's very light, especially compared to copper, so that matters. Shipping, logistics, putting it on a boat, deploying it in the field. It's very easy to work with. And you can carry a tremendous amount of information. And the weird thing about fiber is it can either carry as little information as you want. If the fiber itself is cheap, you can light it with very cheap optics and it really doesn't need to carry a lot of information. Or if the fiber is constrained, you put a little bit more time and effort into the optical system and you can light an enormous amount of capacity, and more capacity than almost any application needs. So it really, the economics of it are very interesting, but it really fills that role very well. And you can really carry a large number of completely independent signals. So there's a mechanism called WDM, wave division multiplexing. You take multiple signals and stack them, and they, in theory, don't interfere with each other. So it lets you grow a network. It lets you do very long distances. You can do thousands, tens of thousands of kilometers without having to do a signal regeneration. And the technology continues to improve. We work with fiber that is 25 years old in the ground that is just as capable today carrying 76 terabits as it was when it was put in, designed to carry 100 megabits, and it will continue to do so. We'll talk about the physics of fiber. So light propagating through vacuum, theoretically the fastest speed that anything can travel in the universe without getting into more complex physics than is necessary. So the speed of light is about 300,000 kilometers per second, which we call c. But when you propagate through a material that is not a perfect vacuum, you propagate slower. And so the ratio of that is called the material's refractive index. So for example, water has a refractive index of 1.33. So it's 1.33 times slower through water than it is through a vacuum. And when light tries to pass from one medium to another and there's a different index of refraction, then you get a reflection. And so that's how fiber works. So it's a mechanism called total internal reflection. So as long as you have two different kinds of glass. You have a core and a cladding. If you didn't have the cladding, fiber wouldn't work. The cladding is what reflects it back into the core. As long as the light comes in at the appropriate angle, it will continue to be reflected through the fiber, and it's very easy to manufacture that fiber cable. So here's kind of a demonstration of how this works using a laser pointer and a big piece of acrylic. So it's the same kind of mechanism. That's just the big version of how your fiber optic signals work. So remember that a lot of what we work with, we work with duplex fiber. So it's cheaper and easier for us to, you have a signal going one way, you have a signal coming the other way, and it's cheaper and easier for us to just throw 2 strands of fiber at the problem. But that's not always the case, right? You can use a point-to-point fiber in a duplex link. You can take 1 strand of fiber and you can send the signal over that 1 strand if you really want to. Slightly more expensive. But the fiber itself is perfectly capable of carrying massive amounts of information. And really the economic question is, at what point do we make the transition through the different technologies? So the most basic distinction when you talk about fiber is multi-mode versus single mode. So multi-mode is designed for, really the point is to be used with cheaper light sources. So it's got an extremely wide core. You don't need as precise a laser. So the optics themselves end up being much cheaper, but it comes at the expense of distance. So what happens is, because the core is so wide, the signal will actually bounce around and you'll get what's called modal dispersion, modal distortion. So you limit your distance from thousands of kilometers down to tens of meters potentially, but it lets you use these very cheap optics. And interestingly, the fiber itself is actually more expensive. So multi-mode fiber is more expensive than single mode, but it's the optics that you get to use are much cheaper. So there's a couple different kinds of multi-mode out there. You've got OM1 and OM2. So these were the original, what's called FIDI grade. So this was the stuff that was designed for 100 megabit FIDI. So it's either got a 62.5 micron or a 50 micron core, and that's the stuff that really starts to break down at 10 gig and beyond. And then you move into the newer generation, the laser optimized. So there's an aqua and a violet colored jacket now for OM4. And that's what you use for your 10 gig and higher signals. And it's specifically designed for kind of what we're doing with modern laser optimized stuff. So you can take a 10 gig signal and take it from 26 meters, and that's on a good day, to going 300 to 500 meters. So you really absolutely require it for 40, 100, and beyond signals. Single mode, on the other hand, is the fiber that you use in everything interesting. So if you're going to go any kind of distance whatsoever, if you're going to do anything real, carry any real capacity, it's going to be single mode. And this fiber has a much smaller core size. So it's between 8 to 10 microns in size. And so there's no inherent distance limitations caused by modal dispersion. So the typical figure that you look at when you talk about a single mode fiber length without any kind of amplification is 80 kilometers, give or take. And you amplify and you amplify and you amplify, but you don't have to regenerate the signal. I'll talk more about that in a minute. But so SMF has a million different classifications. It's even more interesting. So it also has just like multi-mode had OM1, OM2, it has an OS1 and an OS2. But here we're talking about the packaging of the fiber. So OS1 is what's called tight buffered. So that's your patch cables. And OS2 is the kind of fiber that's loose and is blown into ducts. You'll hear SMF referred to as SMF28 as the standard fiber, and so this is a product. This is a Corning product name of one of the early original kind of standard fiber designs. But there's lots of different variants, and each even manufacturer and type of fiber can have slightly different properties. So it comes in things like low water peak, dispersion shifted, non-zero dispersion shifted, bend insensitive, and many other varieties. So here's a picture kind of showing the difference between the core size, just so you have an idea of what it looks like in your mind. And you have this very small fiber inside the core. And interestingly, I wanted to add a slide about this, but one of the new developments that people are pushing towards for higher density fiber is to put multiple fiber cores inside of a single cladding, which is a little weird for splicing, but you can increase that density kind of tremendously, and people are using that to do all their hero experiments of, we did 304 terabits per blah 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 blah. Yeah, you just added more cores inside of the same cladding, but you have the room. You have the room to add 8, 16 even cores inside of a single cladding, and that is technologically where things are going. So there's a lot of different fiber connector types that are out there. You could spend 30 minutes on this topic alone, but I threw in a slide with some pictures just to show the weird things that are out there. The major things that we run across in most data centers, older stuff, SC fiber, newer stuff, LC, and then the higher density, more modern stuff, the MTP, MPO kind of stuff. But there's all these other variants. If you're in telco land, you might be dealing with FC. You might be dealing with the old stab and twist. There's still a lot of that stuff out there. It really depends on your environment and the technology. All right, so basic optical terms and concepts. So we'll start by talking about optical power. So this is basically, you put light into the fiber, and over time you're going to have loss. You're traveling through a non-vacuum. There's going to be some loss. There's going to be microscopic imperfections in the fiber. There's going to be things that are absorbed and converted to heat. So over time, you're going to have attenuation. So that's just the loss of brightness. So we measure attenuation in decibels. So a decibel, which is 1/10 of a bell, is a logarithmic scale unit. And the interesting thing that most people don't understand about a decibel is it doesn't actually say anything itself. A decibel is simply expressing a ratio. You have to compare it against something else in order for you to have an absolute value. So this is what's called a dimensionless unit. So here I'll talk about that. So for example, if you see someone say minus 10 dB, what that means is 1/10 of the signal. And if they said minus 20 dB, that means 1/100th the signal. So every 10 dB is 1/10. And then one that's not exactly precise but is really close is plus 3 dB is double and minus 3 dB is half. But remember, this doesn't tell you double of what. So when you talk about an absolute, like how bright is this thing, you need a reference. So in optical, we use what's called dBm. So this is a decibel relative to 1 milliwatt of power. So if someone says 0 dBm, that means 1 milliwatt. If they say 3 dBm, that means 2 milliwatts. If they say minus 3, that means 0.5. And sometimes I see people, what's the correct way to express 0? And the answer is negative infinity, but no router will actually show that correctly. But confusion between dB and dBm is probably one of the biggest mistakes that you'll run into in the field, because the people they're not precise about what they're doing. So when you're out with test gear, you'll have a dB and a dBm setting, and you'll be, am I looking at this to measure an absolute value, or am I looking at this to measure loss on a cable? And you'll get very different results if you're in the wrong mode. So be very careful of what you're looking at and what you're talking about. So why do we use decibels to measure light? So light, like sound, follows what's called the inverse square law. So the signal is inversely proportional to the distance square. So for example, if the signal travels distance x and it loses half its intensity, and it travels another distance x and it loses another half, so at 2x you're down to 25%, at 3x you're down to 12.5%, etc. So if you use a logarithmic scale to express this, it lets you do your math with addition and subtraction so that anyone can do it, and you don't have to stop and get a calculator and think very hard. Here is a table that you can look at for a handy reference as to what that means. So by the time you're down in minus 50, that's when you're 99.999%. But even down into minus 30, that's pretty effectively a dead signal that is pretty useless. You see it falls off very quickly. So a big problem that we run into when we work with signals over fiber is dispersion. So dispersion simply means to spread out. And there's many different kinds of dispersion, but in the end it results in signal degradation. You end up not being able to distinguish what was a 1 and what was a 0. So in optics, the ones we're primarily concerned with are what's called chromatic dispersion and polarization mode dispersion. So chromatic dispersion is what happens when different frequencies of light propagate through a non-vacuum at different speeds. So that's less of a problem if your channel 1 is propagating slower than your channel 2, but it's more of a problem if channel 1 itself, the start of the signal, propagates differently than the end of the signal. That's where you need that to be fixed so you can decode it. So historically, chromatic dispersion has been one of the biggest limiting factors in everything that we've done in optical, especially in what's called NRZ, signaling direct detect. So the faster your symbol rates, the faster your baud rate, the faster you transition between ones and zeros, the wider your signal line widths. And so the impact of chromatic dispersion increases at the square of the baud rate. So historically, we really kind of limited ourselves to 10 gig because of chromatic dispersion for quite a while. So that's why we went through these all the way up to 160 by 10 gig WDM systems until we found ways to solve that. But it's still a pretty limiting factor. It's the reason that we don't have 1550, 100 gig signals very easily in a lot of optics, and I'll talk more about this later. But so we measure chromatic dispersion in what's called picoseconds per nanometer, and yeah, that's the gist of it. So polarization mode dispersion is the kind of dispersion that happens when different polarizations of light. So remember, light is a wave-ish propagating through space, and it can wave this way or it can wave this way. And if the fiber is not a perfect cylindrical shape, you end up with different polarizations propagating at different speeds. So this is what's in technical terms called DGD, differential group delay, and that's just measured in picoseconds. So this can become a problem. Usually it's not a problem for a very long time until it is a problem, and then it becomes a very severe problem. So for example, a lot of the early fiber that was deployed in like the early 80s that wasn't properly shielded, where they had water get inside, freeze, kind of compress the fiber and make it non-cylindrical. Those fibers are not able to carry modern high-speed signals as a result. But for the most part, you don't run into this until you get into something a little more interested and complicated in the modern world. So fiber has a bunch of different transmission bands. So there's really three that we typically deal with, and four and even beyond if you want to look for new ways to use fiber. So the first one that we talk about is 850. So this is the band of highest attenuation, but it's one that works, and it works well for cheap optics. In some cases, you don't even need lasers. You can use LEDs, diodes. You can do different things. But it's the really short reach, really cheap and easy kind of a signal. And this typically falls into multi-mode at this point. 1310 is it's called O-band, the original band. And so this is the point of lowest dispersion for classic single mode fiber. So this is your intermediate reach applications, your 2 to 10 kilometer kind of stuff. Though we're seeing in modern like 100 gig optics, for example, you have 1310 signals because you need, your baud rate is increased so much that you need to be very close to 1310. And so we put more and more effort into taking 1310 further. And so you can take 1310, in some cases do 80 kilometers with extreme amplification. But historically, the cheap optics, the ones that are mostly out there, it's the intermediate reach role. And then you have 1550, so this is a chunk called C-band. So it covers between 1530 to 1565, and 1550 is the center frequency. So when we have to reference it, we reference it by the center frequency. And this is the area of fiber that has the lowest rate of attenuation. So the signal itself is it has lower loss, but it has more dispersion. So I'll talk about why that matters, why dispersion matters, but typically this is the band that you use for your DWDM applications. Anything long reach, anything high capacity pretty much lives in this space. And then there's a band called L band, which is very similar to C band. It's almost a mirror, and it works almost exactly the same way, but with slightly different physical properties. So you use a different dopant in your amplification to get the same results, but it kind of works the same way. And so for people that are running very, very high capacity systems, they will move into, we'll just double everything into L band, and you can do that, and it works. And there's more exotic things out there. There's germanium doped things, so you can go into other bands. There's all kinds of stuff you can do, but these are the ones that make up the vast majority of the commercial systems that you'll see. So here's a graph kind of showing what the different bands are and why. So if you look at the very top line, you look at the early fiber, it had what's called water peak. So there's little hydroxyl molecules that are inside the glass that absorb certain frequencies of light and make certain bands kind of unusable. And so you see the bands that were picked were kind of workarounds for those water peaks. And then you see the evolution of fiber. So the modern fiber, for the most part, doesn't really have that issue, but it's still there to some extent, right? It's not unusable, but it's of less effect. And so when you're designing a system, it might be the difference between needing to put a hut every 80 kilometers or every 60 kilometers, which doesn't seem like it would be that big a deal, but that becomes really expensive really quickly. So you try to get the most efficiency out of your fiber possible, and that's why we kind of target the bands that we target. So another big thing that you talk about when you're dealing with optical signals is something called the OSNR, the optical signal to noise ratio. So this works like RF, anything else. You have a signal, it comes along certain strength and power, and then you have some background noise. And the background noise can be leakage from other transponders, it can be spontaneous noise from amplification, but whatever it is, when that background noise, you look at the ratio between the quality of the signal and the background noise that is going to disturb that signal. And if you look at modern long-haul systems, OSNR is really the single most limiting factor. It's the thing that you care about the most, and it's the thing when you're designing your transmission system that you're really trying to optimize. And I'll talk more about that when we get into signals. So right now, wave division multiplexing. So we know that light comes in different colors. And what we perceive as white is a mix of many different wavelengths, but what you can do inside of a fiber is carry different signals at different frequencies, and they will, in theory, pass each other, not interfere with each other, and you're able to increase capacity by adding more channels. So the goal is to have a ships in the night approach. They're not touching each other, and you're just adding more and more signal into the fiber, and then the reality is always more complex. So there's a couple different kinds of WDM. The simplest is what's called CWDM, or coarse WDM, and really this is kind of used to mean anything that's not DWDM. It can mean anything under the sun. So there was a historic CWDM, meaning like 20 nanometer spacing. There were CWDM tuned optics. There's like CWDM4 kind of optics that are 4 CWDM colors and a single QSFP that are out there. It's these kind of very loose channels. And then they had, you had like 8 channels to start with, and then you had low water peak fiber that opened up another 10 channels. So there's all of those things. You'll see these in fiber to the home. You'll see these in different applications. But you can also use CWDM to refer to, it's called a 1310 1550 mux. And that's, you just take those 2 most common bands and you put them together as a very simple mux. CWDM really just means anything else. DWDM is the one that is well defined, has standards, has grids, and really means something. So there's an ITU-T standard for it. So when we talk about DWDM channels, we talk about spacing. So if I say, here's 100 gigahertz mux, that means there's 100 gigahertz spacing between center of channel and center of channel. So that defines how many channels. So older 200 gigahertz. So this is basically stuff that you haven't seen in the real world for a while, but it's out there in theory. This was kind of the original WDM technology. And then 100 gigahertz is the stuff that is probably still the most common. It's used in metro. It's very cheap. It's very commodity. So you end up with about 40 to 48 channels. So technically you can get 48 channels, but what ends up happening is you can't really fit 48 LC connectors on a 1U panel very well. So people just turn it down into 40, and they'll do it in various ways. They'll clip the ends, or they'll do it in blocks. So if you do like a block of 5 channels and you skip one, then what that lets you do is you could have different muxes. You could have a mux of band A and a mux of band B, and you skip that channel in the middle where they might overlap, and so you can take multiple small muxes and feed up into big ones. But for the most part, it's that 40 to 48 channel thing. Then you have the 50 gigahertz. So if you look at the evolution of the technology, where this went, you went from 200, 100, you went into 50. That's still very, 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 very common for your commercial systems, your long haul systems. And then we moved into 25, and this is right in the era when we were trying to get as much capacity, but we were limited in our technology. And the only thing that we could do was add more and more and more 10 gigs. And you saw that move very briefly, and then you saw that back away. And so the modern way that we handle this, the way that works is you actually have you have coherence. I'll talk all about that technology, but you have these very wide channels that are using wider and wider bands, and that's how you're able to step up the signal. And so we've moved back into a world where most modern signals require something like 62.5, 70, 75 gigahertz. So we've moved into what's called flex grid. So in a modern system, there's not these hard defined channels of this mux that you put in once and hope that it stays there for 10 years. You have the ability to map the channels however you want, with varying degrees of cost and pain associated with that. So here's a kind of comparison looking at the different channel sizes just so you get an idea. So you see the entire C-band where you can have 80, 160 channels and how small that is compared to, you know, 2 CWDM bands. So it gives you an idea of kind of the perspective of these things. So what are the advantages to each? So CWDM, the whole point here is that you get to use these cheaper, less precisely, mostly cooled lasers. So the signal itself isn't actually you're not transmitting light at 20 gigahertz of spectrum. What you're doing is the signal is free to wander around, and so you don't have to spend as much money on your cooling system to keep the laser as precisely tuned. And cooling actually ends up being a significant component of the cost of the optics and how that works. So DWDM, obviously you get far more channels, you get much better engineering, you get to stay completely in the C-band. So the advantage of staying in C-band is that's where you have amplification through what's called an EDFA, an erbium doped fiber amplifier. But yeah, that's the gist of it and why you use it. So remember I talked about all the other different kinds of wave division multiplexing. So you've got that 1310, 1550 mux. You have 4-lane gray optics. So for example, usually the way this works is whenever you move into a new speed, so you move from 10 gig or 40 gig to 100 gig, or you move from 100 gig to 400 gig. The way that it works early on is you don't actually have a native 100 gig signal. You don't actually have a native 400 gig signal. So what you'll do is you'll have multiple lanes, both electrically and optically, that get combined to make that signal. So for example, when 10 gig first came out, we didn't really have the technology to cheaply, easily do a whole 10 gig signal, but we could very easily do 4 2.5s, and so we had a standard called LX4. 40 gig, when you look at 40 gig LR4, what that actually is 4 10 gig lambdas talking electrically out 4 electrical connectors. 100 gig LR4, same thing. They made the grid a little bit tighter because they have to stay very close to that 1310, but it's the same gist. You have these 4 lanes. As you move into 400 gig, you see a lot of very similar stuff happening. And then you also have what's called single strand, or BX, or bidirectional optics. And so this is you take 2 frequencies that are slightly different, because if they're the exact same frequency, you can have interference from reflections, but you take 2 different frequencies and you put them over the same cable. And so this can let you either work with a single strand system, or it can let you double your capacity without having to install a mux, rack anything, cable anything. So you'll see a lot of those used in the wild. So we'll talk a minute about the channel terminology, because this starts to matter as we look at the real details of DWDM and WDM in general and how it works. So remember when I said we talk about 100 gigahertz mux, that's the channel spacing, that's from 0 to 0. So you also have the channel passband, that's the total amount of signal that is sent before you start to be clipped by the edge of the mux and then the other channels that are nearby. And so you'll have different levels of interference. You'll have adjacent channel isolation. So what's the amount of signal that I get before the next channel over starts to interfere, and then what's the amount of isolation that I get for the entire system and the other 30 channels that are sitting over here. And these start to add up. So what's inside a mux? It's really cool because it's a really simple passive unpowered device that combines or splits multiple colors of light from a common fiber. So it's short for multiplexer. You'll hear it called a filter or a prism. So a filter is how it actually works. You take light and you kind of filter it out, but people kind of understand conceptually that a prism takes light and splits it. So you'll see that. But a complete system requires 2 units. You need a mux and a demux for the TX and the RX. And usually you'll see that sold as a package. But like if you crack open one of these little boxes, you'll see that there's 2 individual units. And there's a TX and an RX. And that's how you're doing it. Another kind of passive component that is really fundamental to a lot of things is what's called an OADM, an optical add-drop multiplexer. So what you're doing here is you're selectively adding or dropping certain channels without disturbing the other channels that are nearby. So muxes are what's your big endpoint. It's where you break out all of the channels. An OADM tends to be a node on a ring where, for example, you want to access a channel, 2 channel, 4 channel, whatever that is, but you want to let the other 30, 40, 50, 80, whatever channels go by untouched. So it ends up looking like this. You have a component called a circulator and an FPG, and I'll talk more about them in a second, and that lets you add and drop that channel without disturbing the others. The way that we do this, there's a couple different technologies. So an FBG is what's called a fiber Bragg grating. And this is pretty cool technology because what's happening is you use a really powerful ultraviolet laser and it literally etches little patterns into the fiber in very specific ways. And what that does is it causes reflections. So if a light of a certain target frequency comes in, and it hits this FBG, it will be reflected. And if it's not that target frequency, it will be passed. And so this is a fundamental building block of a lot of other components, and it is used for tons of things. You have another technology called TFF, thin film filter. So this is commonly used in your like 16 channel count muxes. It's out there, but it's not as pervasive as it used to be. And then the big one for high capacity systems is what's called an AWG, an arrayed waveguide grating. So what's happening here is you have literally 2 big prisms. And you're taking the signal and you're spreading it out and you're letting it constructively and destructively interfere with each other on this big long strand of fiber that goes certain measured precise distances. And when it all recombines in a certain way, it's broken out into all of these channels. So it's a really cool amount of engineering that goes into it. It's usually a black box that no one ever opens because once it's out of the factory, you'll never be able to touch it. But the modern systems are what's called an AAWG, an athermal system, so you don't need to cool it, doesn't need power, doesn't need monitoring, nothing. It's literally just a passive device. And these are what you use for your higher count systems. And so as you move beyond 40 channels, so if you move into an 80 channel, 96 channel system, typically what that is 2 40, 48 channel systems stacked on top of each other. But so that 40, 48 kind of channel count is the fundamental building block of that space. So then we move into a thing called a reconfigurable OADM or a ROADM. So think of this as just an OADM, but something that you can configure in software. So typically that's built around a component called a WSS, a wavelength selective switch. And there's a couple ways you can do that. There's the 2 basic architectures are what's called a broadcast and select. So you take your signal and you split it and you just broadcast it to every possible direction, and then you have a WSS on the other side that picks out the one that you care about and discard the rest. And then the more sophisticated version is the route and select, and that's where you have a WSS on both ends. So you're actively controlling what you send and what you select and receive. And it lets you do dynamic channel mapping. So this is where you get to sit in a NOC and have a pretty GUI and click a button and move a wavelength across the country, and it's lovely. But there's a lot of downsides to that. It's very expensive. There's a lot of amplification. There's a lot of very complex components that go into this. They're at this point very difficult to get because of supply chain. So when we talk about ROADMs, you'll hear a terminology called ROADMs degrees. So a degree is basically a possible direction that it can be steered. So if I'm sitting on a switch and I can go north, south, east, or west, that's a 4-degree ROADM. And what'll happen is people will design systems where you can just add another card and you can expand your degrees. And the way that works is every degree, every possible avenue of selection is this wavelength selective switch and a big mesh. So you end up 1 degree has to have a big fiber mesh to every other degree. And so as this expands, you end up with this big giant fiber spaghetti, and you have to create all kinds of things to optimize that. But that's how it works inside. It's a big pile of, I want to take this wavelength and send it there. I want to take this wavelength and send it there. So the classic OADM, or what people call a fixed OADM or a FODM, the way that works is you go out and deploy it and you don't get to change it. So it's really great for, let's say you build a 10 node ring and you have 40 channels, and so every node is going to get 4 channels, right? Give or take. So if that's enough capacity for you, if you're the one controlling the capacity, it's a really cheap, effective way to do high bandwidth. And you can, I've got 4 channels going to this node over here, and I've got 4 channels going to this node over here, and so I'm great. I can work with that. But if you're selling to customers and you're trying to sell wavelengths, and so all of a sudden this node over here blows up, becomes really popular, and this node over here isn't very popular and doesn't get a lot of business, that's where you'll spend all of your time redeploying hardware in the field and trying to optimize that. And so that's where you move into the world of a ROADM, so you can kind of scale that up on demand. So you're striking the balance between the most efficiency and the price per bit versus the most efficiency in the, I want to be able to deliver any capacity to any point between any point. And if you're willing to make that trade-off, if you're willing to say, well, I know that I have a hub that all of my capacity is going to go to, I don't want random node over here sending 100 terabits to random node over there, that's when you move into different designs. So the evolution of the ROADM is kind of interesting, because you can see it's getting more and more complex over the years. So your basic ROADM, it's literally a WSS that then goes to a MUX. So you say I'm in a node here and I want to send something north, I want to send something east, I want to send something west. What that actually breaks out into is, here's my 40 channel fixed MUX. And so I want to use channel 1, I plug something into channel 1, I run a cable, I run it into an optic channel 1. It's very fixed. And that is the cheapest way to do it. But obviously it's very difficult. If you want to add capacity, you're sending people out in the field, you're plugging in cables, you're moving stuff, it can be a real pain. So we move into the world of a colorless ROADM. And when you're doing coherent signals, you don't actually need to put channel 1 into a MUX that's labeled channel 1 that goes to an optic that's channel 1. You can actually, your optic itself is dynamically tunable, so you can make the optic behave in whatever frequency you want it to. And you can plug it into not a MUX, but a splitter, because a coherent signal can kind of lock onto the signal that it cares about and discard all the others. So that was the early generation of this colorless ROADM. Was that you had that level of flexibility. You didn't have to go out and recable the optic every time you wanted to do stuff. And then the modern version of this is what's called a CDC ROADM. So it stands for colorless, directionless, and contentionless. So colorless means obviously any channel can be dropped on any port. Directionless means any channel can be sent in any direction, and contentionless means you can reuse the same channel across multiple pieces of the ROADM itself, and you're not going to be blocked because this path over here is using it. Your ROADM itself is not blocking your ability to consume every channel on every line system. And these are the most powerful, but also the most expensive. So what's the point? The whole point of the CDC ROADM and where they're trying to go in this space is to make this something that you can dynamically control in software. So imagine you've got a transponder that you could repurpose. So at one point of the day you might turn up capacity towards Asia, and then later in the day you might turn up capacity towards Europe, and you can dynamically move that around without having to buy 2 transponders and have a bunch of idle capacity sitting around. So you're looking for that evolution of, and so where this moves into is something called, originally it was called GMPLS, Generalized MPLS, and it moves into a new technology called PCAP, Path Computation Element Protocol. So you're taking the elements of traffic engineering that you would do in MPLS, that you would do in segment routing, where you say, I know that this router needs to send 50 gigabits to that router, and you're tying it into the optical layer. So the optical layer can now respond to that dynamic traffic use and go, okay, I need to spin up another transponder. And there's varying degrees of success on that, but that's where the industry is trying to push towards. That's what the modern life systems are built for. and it definitely has its advantages. But what actually goes on inside of a modern CDC ROADM? Well, here's kind of a breakdown. So you come into this thing, the first thing you have to do, amplify your signal. You amplify, and then you go into a WSS. You go through like a 1x20 WSS, and that's going to take a huge signal hit. So as soon as you come out of that, you have to go into another amp. And remember, you have to, every possible WSS exit has to go to another degree. So if you've got a 1x20, you've got this big mesh of, you need an array of amplifiers. So you have these high density multi-channel amplifier arrays that you take the signal, you amp it, you steer it, you send it over here, then you send it out what's called a multicast switch. So you take this thing and you broadcast, you split it 16 ways and you send it down to a thing, and it's very, very complicated, and you're doing a lot of amplification a lot of times. So that's that trade-off of, you get that dynamic, I can just sit and click a button and move a wavelength and everything is great, but you've paid for it both in cost, complexity, and optical signal. One thing that you'll hear talked about is what's called a super channel, and that's what happens when you want to deliver something that is bigger than what a single carrier can deliver. So you use a super channel to kind of pack multiple carriers together, and so that you can think about it as a single channel. But like, this is an example of, let's say you wanted to send a 1 terabit. This is an old slide, but if you wanted to do this with a single carrier, you need a 320 gigabaud system, and it's just impossibly complex, doesn't exist, not going to happen. But what you can do is split that up into multiple different carriers, pack them very tightly. You can even treat them as, here's a really big channel, but inside of it is multiple subcarriers. And that's actually becoming more of an evolution of technology. And you see the same thing in 4G and 5G, where what's actually happening is you have many different subcarriers, and each subcarrier can react to the different properties of the medium. You're seeing that direction happen in fiber. So fiber usually ends up being 10 years behind whatever's happening in RF, but you see the same kind of progression happening in fiber, where, hey, we can work with many different smaller signals, and that's where things will go over time. So remember I said early on it was about fixed channel sizes, and so it didn't really matter what you sent. It was going to be like, here's a 50 gigahertz grid, and maybe you send a 1 gig signal through, maybe you send a 10 gig, maybe you send 100, maybe you send a wide channel, maybe it's narrow. It doesn't matter. It is what it is. And in a modern system, flex grid system, you can dynamically tune down into the very small increments. So you've got a really big, wide, modern signal, you can accommodate it. You've got a whole bunch of small, older signals, you can accommodate it. The downside to that is, once again, complexity and cost. So flex grid systems, a passive mux can be on the order of hundreds to $1,000. A flex grid system can be 10 times that or more, and it's deeply integrated into your complex ROADMs and everything else. So there's a trade-off. So other optical components that are out there. So dispersion compensation. So remember I said dispersion, you've got your signal, it's spread out, and so now you need to do something with it. The early generations of how this was done was just a big spool of fiber inside a box, and this fiber was engineered to do the opposite of whatever the line fiber was. So when the line fiber would spread the signal out, the fiber in a spool would compress it back together, and I just sent it over a 50-kilometer span. I put a big spool of like a 7-kilometer thing of fiber that's designed to fix 50 kilometers worth of dispersion. It comes out the end, and there you go. And so that ends up adding something like 20% to your fiber distance, so it increases latency, needs more amplification, etc. And then the way that newer designs handled this is through an FPG. So you design your Bragg grating to actually cause or correct dispersion as it's reflecting the signal. The nice thing about that is that it's no latency hit. There's less power loss. There's all of these nice things. The downside is that it's not as easy to do wide channels. So in a modern world where you have wider and wider channels doing higher and higher gigabauds, it becomes increasingly difficult to work with that design. So you move into tunable dispersion compensation, where you basically have heated or cooled components that are causing slight variations in how the FPG is working. But it's ultimately, like I said, it's very difficult. Whereas if you've got the fiber spool, it's this nice smooth slope. You can send whatever signal you want, and you don't have to be aligned to a specific grid. Whereas the FPG is actually created on a specific grid, and your signal has to be aligned to that. So optical switches are these cool little components, and you can do this mechanically too, but the ones that are actually interesting are the little micro mirrors and 3D MEMS stuff. So basically you have this big grid and these little micro mirrors, and you can, through software, click a button and it will steer the mirror and it will move the light so that it goes from port 1 to port 2. And so you'll see these in products. These are great in labs. These are great in lights out environment where you don't have to go out and recable things constantly. They tend to be too expensive to do in production in most systems. But you'll see them as components inside of other things. So even something as simple as like a 1x2 or a 2x4 switch, where you literally just go A or B. You pair that with a 50-50 splitter, and so you can get I have 2 fiber paths, and I will use whichever one is working at any given moment very simply, very cheaply, and without having to add a lot of cost to your transponder. So you'll see them in all kinds of applications. So the WSS, this is a really complex, interesting, high engineering component. You've got these little micro mirrors, you've got these liquid crystal and silicon things. It's beyond what would normally be addressed at NANOG, but just understand that these are the components that are going on inside of a WSS to make this possible, so that you can steer your wavelengths. A circulator is a cool component that you pretty much never see as an end user, but just so you know what's happening. So the way a circulator works is there's 3 ports. And so something comes in port 1, it goes out port 2. Something comes in port 2, it goes out port 3. Well, why would you want that? Well, you take that and you pair that with an FPG, and that's how you get your OADMs and a lot of these other components. So you see an FPG, the way that works is that tiny little etched piece of fiber that will reflect a certain signal. If it's reflected, it'll come back to my circulator and I'll drop it and I'll be able to consume it in this network. If it's not reflected, then I pass it on, and that's an OADM. So like I said, it's just an internal component, but when you start to think about how these things are designed and what they're aiming to do, it's good to know what it is. So optical splitters they do exactly what they sound like they do. They split a signal. So some really common examples of that. So like I said, a 50-50 splitter. So you take your signal and you literally just split it 3 dB, and you send half of it this way and half of it this way. And then you just, on the other end, you have a switch looking at it, and it goes, I will use whichever signal is strongest. And so you get that easy, cheap failover into a building without having to deploy a lot of other complicated systems. You'll have a 99.1, a 98.2, a 95.5 splitter. These are your optical performance monitoring. So what will happen here is, let's say you tap 5% of the signal as you're going through your EDFA, as you're going through your MUX, whatever it is. You can do things like you can come along and plug in a spectrum analyzer and see what's happening. You can actually have little spectrum analyzers integrated into your gear, so you can look at what signals are going across my network, what's the OSNR, what's the quality, what's the power, are they balanced? It's really cool. Obviously you pay for that, but it gives you a lot of flexibility in your engineering. And then you'll have like a 1/n. So typically this is powers of 2, and this is like a multi-point distribution. So for example, used in cable TV, you'll have like a 1/32 splitter. And what's happening here is you literally, it's broadcast, and so you take the signal, you have a very powerful amp, and then you split it 32 ways and you send it out to the 32 different units. So now I'm going to talk about optical amplification, which is really complex and really interesting and pretty fundamental to everything that we do in optics. So the point of an optical amplifier is a way to increase the intensity of the signal. So you had a light, it got dimmer, now you need to make it bright again, but you don't actually want to take that light, decode it into electrical, and then re-encode it, because that turns out to be very expensive. So there's different kinds of amplifiers that you'll hear things talked about as boosters, preamps, and inlines, and these aren't really strict roles. There's not actually a difference. Like, this is a different technology for a booster. It's a slight variant in how they're built, and so you'll have an EDFA or an amplifier that's better in this role or better in this role, but it's ultimately up to you as the network that you're building as to what you do with it and why. So a booster is designed for high total. So you put a booster when you're transmitting. So you've got a signal coming. You want to make it as hot as possible before you put it out in the line. There's your booster. A preamp is what you have on the receive side. So you've got a signal coming in. It's kind of weak. You want to make it brighter so that you can decode it easier. It's designed for that low power level, low noise. And an inline is just something that kind of strikes a balance in the middle. And it's designed not to really decode the signal, but then to just amplify it and pass it on to another node. So the way that this works, the most common kind of amplification that's out there is what's called an EDFA, erbium doped fiber amplifier. So the way this works, you have a little piece of fiber, and it's not very big. It can be 10 meters, something like that. And in this little piece of fiber, they come along and they dope. So in the manufacturing process, they have snuck in a couple of little erbium atoms, and it's very, very few, but they're in the glass. And what happens is you take this loop of fiber and you add another laser to it. So in EDFA, you use either 980 or 1480. And these are the frequencies. The reason that we use erbium is because that's the thing that does what we want in C-band. And there'll be some other element that'll do the exact same thing in a different frequency. So the 980 and the 1480, these are the laser powers that will come along and excite the erbium ion. So you'll have these electron shells that'll jump to a higher energy state because power has been put into the system. And so now that you have these erbium ions in this excited state, you have your good signal come in, and as it comes in and hits these erbium ions, the electron will decay to a lower energy state, and it will emit a photon, and it will be a clone of the signal that you put in, and that's how you amplify the signal. So the reason you have 980 and 1480 is you just have two different stages. So if you put in 1480, that's your quasi-stable state. That's where your amplification is really happening. And if you put in 980, it will immediately decay to the next level down, and same deal. But it's that kind of mechanism. And so if you actually look at the construction itself, you have that loop of fiber. You have the little filters on either end, so you make sure that you don't leak your pump laser out into the world, so it will never go out either direction. You inject your pump laser in, and all the amplification happens inside that little spool of fiber, and that's what's called a lumped amplification system. So that's awesome. Why can't we do that forever? Well, you have a thing called noise. So in addition to amplifying the signal that you want and creating these great photons, you will inherently create what's called ASE, amplified spontaneous emissions, which is noise that you don't want. So the reason for that is once you get that erbium ion into an excited state, you get this electron up, you have about 10 milliseconds for a good photon to come along and hit it. And if within that 10 milliseconds a good photon does not come along, it will spontaneously decay and emit a bad photon. And that bad photon is noise that looks the same as your regular signal and will eventually make it unusable. So the way that you want to think about this is the stronger the signal when you amplify it, the better your amplification will be. But after enough amplification passes, so here's an example of kind of what EDFA noise looks like. So this particular curve, you see the two spikes that are the two good signals, and then everything else in here is noise that comes from the EDFA process. And it's stronger in certain bands than others. So like I said, why does that matter? So I don't think this is quite the right way to visualize this, but I was trying to illustrate that it really, really matters, because if you take a signal and you amplify it before it gets too weak, your OSNR will stay beautiful. It'll stay nice and clean. But if you wait, like the more and more you wait, so as you go into, you let it go to neg 10, you let it go to neg 15, you let it go to neg 20, you see this rapid drop off in OSNR that you get as you go through more EDFA hops because of that. And so that's what you're designing against when you're trying to make this work. Another kind of amplification is called Raman amplification. So this works through a principle called stimulated Raman scattering, and in certain areas that's a bad thing. So that's what's called a nonlinear effect that we don't like later in the talk, but for right now it's using it in a good strategic way to do something that we do want. So what happens here is rather than take the signal and make it brighter within this very small loop of fiber and then send it back out, what we're doing is taking the Raman pump and sending it back into the line. So you take a laser of a certain non-transmitting frequency, you send it backwards into the line at very high powers, and when your good signal comes along, it transfers power. So that pump laser gets weaker and your good signal gets brighter. And like I said, you can do it lumped, but you shouldn't. It's really used in a counter-propagating way. Well, why do you want that? So let's take a look at how this works with an EDFA-only amplification. So there's two things that you don't want to do when you're transmitting. You don't want to transmit too much power, and you don't want to transmit too little power. If you transmit too much power, you get something called nonlinear effects. It's basically high power problems, and it will rapidly degrade your signal, and there's a limit to how much power you can put into fiber before it literally spits it back out and says no. And then you don't want it to get too low, because that's when you start to add noise and start to have an unrecoverable signal. So if you look at, here's my nice steady curve. I transmit, I got this nice high power level, and it gets lower as it goes through the fiber, and then I come to an EDFA and I make it bright again. The only way to make a span of this distance work is to go into the two zones we don't want to go into. All right, so we transmitted really hot and we had to amplify really weak. But if you add Raman, counter-propagating Raman to that, here's what happens. You get to transmit at a much lower power, so you get to stay out of your bad nonlinear zones. And then as you get towards the end, what happens is rather than go lower, that signal just slowly starts to get brighter. So by the time it comes into the next amplification stage, it's already a much higher power signal. Now you can apply your EDFA again, and you get to apply less amplification, less noise. You had a stronger signal coming in. You don't go into the nonlinear zone again. It's a tremendous gain. So what does that look like? Well, here's an example of 21 dB OSNR, 7 hops. So you literally take a signal that would have only gone through 7 amplification passes and turn it into 20 in the exact same system. So that's a tremendous gain, because if you had to sell service and you actually had to go, you would have had to regen that signal 3 times. That would have been terribly expensive. But here you change your amplification design and you're able to take that same signal, carry it much further, or even if you're not carrying it that far, when it does come out, it's got a higher OSNR, so you can get more bit out of it. But when you do amplification, you really have to concern yourself with power balance, because amplifiers, the whole point of what you're doing is you have all these channels, and they, to some degree, have to be balanced. If they're not balanced, what happens is the high power channel steals all the power, and the low power channel doesn't get any. So it's actually a problem, and one of the reasons that you can't just sell spectrum is if someone comes along and injects a signal, a really bright signal that you don't want, it'll just destroy all of your good signals. So you have to look at this. So the first thing that happens inside of any amplifier is you have a gain flattening filter, GFF. And so that's just basically a little FPG that's designed when they make the EDFA to kind of match the EDFA profile so that it will try to flatten it out a little bit. It won't be perfect, but it'll take a first pass at it. And then after you go several hops, you will inherently, one signal will get a little bit stronger, one signal will get a little bit weaker. And eventually you'll have to do what's called DGE, dynamic gain equalization. So probably the easiest, most common way to do this, and why there's a lot of ROTEMs out there, is you run it through a ROTEM. So the whole ROTEM process is effectively re-power balancing and reshifting every channel independently. So that's how you come out with a nice flat gain. That's how you do your long haul systems. Amplifiers also really care about the total system power. So they care both in what they can output and what they can input. And this is kind of one of the most fundamental things about their design, and really informs everything that you do and why you do it. So let's say that you have a single channel. It's coming in at 0 dBm, so you've got 1 milliwatt of power. Great. So now you put a 40 channel mux on that, you do the same thing, you've now got 40 milliwatts of power, you've got a plus 16 dBm system. So if your amplifier's max power input is neg6, for example, let's say that it's a, I'll make up a theory, 15 dB gain amplifier that can output 21 dBm maximum power, and so each channel must come in at, or yeah, no, even the whole system must come in at neg6 because it would blow out the amp. You have too much signal. So what that means is that each channel has to come in very weak. So you look at that and you go, okay, in a 40 channel system, each channel must be below -22 before it goes into the EDFA, or it blows the whole thing up. And so what you end up having to do is, if it's not weak enough, you have to make it weaker so that you can amplify it again, which is counterintuitive, but that's what you have to do to make that system work. And remember, this is a potentially dynamically changing system. So you've got this system coming along, and then someone comes along and flips off power to the rack, and 40 channels die, and so the power in the system completely changes, and you have to react to that and make sure that that's good. So the good EDFAs will actually have a feedback loop, and they're monitoring and making sure that they're adjusting the power mode. And the really good EDFAs are ones that actually have an out-of-band communication to the EDFAs around them, that are talking to them, saying, what are you outputting, what's the signal quality, what are we doing, and coordinating with each other, coming up with that design. All right, so more optical concepts. We have a thing called forward error correction, or FEC. So the way to think about FEC is kind of like RAID for your optics. You're adding a little bit of extra redundant information so that you can computationally recover from any errors. So in practice, the way that works is it lets you lower the required OSNR, in which you would have had a signal that you couldn't decode, and now you can, and so that lets you do more with it. So for example, you can take a 10.325, so that's a 10 gig E, that's what it's actually transmitting, is 10.325 with overhead, and you pad it up to 11, so there's a 7% overhead, and now you take what would have gone 80 kilometers and you can make it go 120, because you can recover from a weaker signal, or one with more dispersion. And where this really matters is when you've got these old systems, these brownfield systems, because if you want to go deploy new technology, great, but you probably can't move your huts. You probably can't redo the way the fiber is connected. You have a lot of systems that are out there that you have to work with. And so FEC lets you do that. It lets you keep growing that. And it's become very baked into almost everything that we do. So the first gen FEC, the really simple FEC, the FEC that you find pretty much everywhere on every box that you'll ever buy at this point, is what's called RS FEC, Reed-Solomon FEC. And so that's like 6% overhead, and you get 6 dB of net coding gain. And then there's newer generation, there's eFEC. And then the newest stuff, the things that are happening in modern systems, is what's called SD FEC, soft decision FEC. And here you're adding a tremendous amount of overhead. You jump from 6 to 7 to now we're up, oh, okay, here's 25% overhead. Well, why do we do that? Well, it turns out that extra couple of dB of gain is tremendous. That's the millions and millions of dollars of difference in transponders. So it's worth putting a little bit of extra overhead into that signal. And like I said, it's really baked into, at this point, it's firmly a part of almost every optical standard that you will find, with a few exceptions. So the very original standard, so if you look at like 100 gig, for example, one of the very first things that was standardized for 100 gig was LR4. It's a very simple, and it was designed in a world before we actually knew, is FEC going to be available on every host board or not? The downside of that is that in order for LR4 to work, it has to be very tightly packed around 1310, and that makes it more expensive. You have a more precise lasers, you have better cooling, you have a tighter mux. The modern version of that is you get to use a wider mux that doesn't need to be as precisely cooled, and you cover it in FEC, and it's 40% less than the cost of LR4. So in the vast majority of the world, if you look at the shipment of optics, most of the world uses things like CWDM4, 4WDM, which is the modern evolved version that's much cheaper. But for some reason, the internet side, the peering, the transit side is still fixed on the first thing that we heard about, which is LR4, which is actually not as efficient and doesn't take this into account. But almost everything else, SR4, all of your 400 gig stuff, all of your modern stuff, all has spec very much baked in there, and it's just a part of the standard now. So here's kind of what this looks like in a graphical form. So if you look at, this is a bit error rate. So as it gets higher and higher, it becomes unusable. So you want your bit error rate to be very, very low. And over here on this blue line, this is the OSNR on the x-axis that we needed in order to get a very low bit error rate. So we needed to have a very good signal. We need to have an 18 dB OSNR signal in order to get this lowest bit error rate. And with better and better and better effect, what happens is it pushes that bar over. So now I was still fine. I have an 8 dB, which is a tremendous difference. Remember, this is logarithmic. There's a tremendous difference between 18 dB and 8 dB in terms of signal quality, and I'm still able to work with it, and I'm still able to decode and transmit that signal. There's another thing called OTN digital wrapper technology, G709. So this is kind of the modern version of SONET and SDH for wavelengths. And really what's happening here is you're kind of making a system that is generic. You aren't fixed to, like when the original WDM systems came out and it was for 10 gig, it was for OC192. And then when 10 gig E came along, it was like, oh, no, we don't support that. None of our transponders do that. So OTN is the fix to that, so that you can carry the wavelengths through your system and know something about what they are. You can even mux them up into different things without being so tied to a specific technology. But you'll hear that run across. It's typically more important for carriers, and typically nobody cares about it at the data center or even packet kind of level. All right, so types of single mode fiber. This is a nice long one. So I already talked about how single mode is used for essentially all of your long reach fiber applications. The standards that go into single mode, so you've got your standard, that's called G.652. And there's newer revisions, so there's G652B and C and D and things like that. So G652D is the current version of that standard. And that's your standard SMF. That's as baseline as you get. There's so low water peak actually got pulled into standards. So if you look at like modern fiber, it is low water peak fiber. It's G652D, and that's fiber that's designed to not block some of those bands that you might want to use. Then you have a thing called dispersion shifted fiber. So this was fiber that was designed so that the lowest point of dispersion was moved from 1310 to 1550. The hope being, oh great, we'll transmit with no dispersion and with low loss. It'll be fantastic. And it turned out not to be. It was a terrible idea. So then there's G654, which is the fiber that's for subsea kind of stuff. Then after they figured out that 653 was a terrible idea that should never have been done, they're like, oh crap, revert. So they came up with non-zero dispersion shifted fiber, which is similar, but you don't get that point of zero. So it turns out we actually like dispersion. We need dispersion. Dispersion is important. But when this was originally designed, people didn't know that. This was before the invention of DWDM. I mean, really, DWDM is not that old. Like, this was deployed commercially in 1998. This is newish technology that in some areas changes radically, and in other areas doesn't change at all. And then you have G657, which is the standard for bend insensitive. So it's your data center patch cables that people play around with, and it doesn't need this perfect bend radius. So your standard single mode fiber, like I said, you'll hear it called SMF28. It might not actually be, but that was a common problem. And there's SMF28E plus low loss. There's all these new versions of the same gist, but you'll also hear it called NDSF, non-dispersion shifted fiber. So it's G652, and this was originally designed for that 1310 band, and it has dispersion in 1550, but the lowest attenuation. And so ironically, the oldest kind of fiber has come full circle to being the kind of fiber that we actually like again. So it's interesting to watch the evolution of the technology. So the low water peak fiber, like I said, they just engineer the glass so that it removes less of that, take out some of the hydroxyl molecules, and you have less attenuation in some of these bands. So the dispersion shifted fiber, like I said, you need dispersion. It's the best way to describe this. When you have dispersion, so you have a signal come in and you have what's called walk-off. So you start to spread the signal out a little bit. If you don't spread out the signal, what you have is this power entering the exact molecule at the exact time, and that causes your nonlinear effects. So you want a little bit of dispersion, so you spread that. So at any given instant, that exact photon is not passing through that exact atom. That ends up making your signal much better, and it really matters for WDM systems. Sorry. So like I said, they deployed some of this stuff out there and then realized horrible, and it hasn't been deployed in a very long time, but you'll still find it in the field sometimes. So non-zero, what they said was, all right, we like the idea, because this was designed in a time when 10 gig was what you were trying to accomplish, and dispersion was your biggest enemy. So we like the idea of lower dispersion, but we don't want it to be zero. So we'll move the point of zero dispersion outside of the band that we want, but we're still down. You take it from 17 picoseconds per nanometer down to 2 or 5 or something, and this will be good. And so you'll have two different slopes of fiber. You'll have the transmission fiber where the signal spreads out, and then you'll have the compensation fiber that's matched to this. And so it actually has to be brand matched. Like if you have Corning fiber, you need a spool that is designed to match exactly that Corning profile so that it balances out. And if you buy Lucent fiber, it'll be something slightly different. But that was the theory. So this was, like I said, this was very much early 2000s 10 gig kind of signals. G654 is the ultra low attenuation stuff, and so what's happening here is it's actually ultra wide core. So when you're doing subsea, you're deploying this multi-million-dollar thing that you hopefully won't ever go touch. It'll all be built in a clean room and engineered and rolled out, and you hope that it's going to last for a really long time and carry a whole bunch of signals, and over time carry much better signals than you ever put in. So when you design for that, where you can't just go send a text and swap out a card, you design for high power. So you want really wide cores so you can get really high power so that you do less noise when you do your amplification. That's what that exists for. G657, like I said, is the bend-insensitive fiber, and there's a bunch of different standards on that. But most fiber that's out there is actually better than the spec, the official spec, the minimum requirement. But if you really care, you figure out what kind of fiber it is, and you go pull the spec sheet on it and look it up, and you can see the exact details. So here's an example of like dispersion rates of different fiber, right? So true wave product versus a leaf product versus a Teralight product, and what that looks like. But so for regular SMF, 17 is the kind of the middle of the band standard for dispersion that you'll see. All right, so now I'm going to talk about nonlinear impairments, otherwise known as high power problems. So if you don't transmit at high powers, you will never see these problems. Full stop, end of statement, you're good. So what do I mean by high power? Well, it depends. As a rule of thumb, it really doesn't matter until you get above +4 dBm per lambda, give or take. So the nonlinear impairments, they categorize as the following. So you have a classification called stimulated scattering, of which you have SBS and SRS, so stimulated Brillouin scattering and stimulated Raman scattering, and then you have something called the Kerr effect. And what's happening there is the light itself, the intensity of the light, is actually spontaneously, momentarily changing the refractive index of the fiber. And that causes things called four-wave mixing, self-phase modulation, cross-phase modulation, probably a whole bunch of other stuff that I would not dare to speak on. So SBS is probably the first one that you hit and deal with. And it's pretty cool because what's happening here is when you put too much power into the fiber, it's literally causing an acoustic vibration at the atomic level of the glass. And it happens, it sets up a frequency in such a way that it causes reflections back. So it's basically the fiber is saying, I can't take any more power. It has to go somewhere. It spits it back out where it came from. And so at a certain point, this can actually cause damage to the transmitter if you spit too much power back out. And this is the stuff that you run across most commonly in your, well, I just took a 10 gig signal and I made it really bright, and why doesn't it work? Well, because of this. And modern signals, coherent signals, things that kind of dither the signal out over wider, blah, 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 blah. It helps, so it's not as big of a thing in a commercial, well-designed system, but it's very much the thing that you'll hit as you like try to just take a signal and amplify it, and you haven't designed it properly. So SBS also requires long fiber. So if you do something that's really bad that would cause SBS, but you do it over a 1 meter patch cable, it actually doesn't matter. But you put it over 20 kilometer span and it matters. And it starts to fall off and it really maxes out at 20 kilometers. So once you're above 20 kilometers, it doesn't matter. It's the same as though it was 20 kilometers. But the length of that span is what's causing that effect to happen. So you have to remember that you can sometimes get away with stuff in short distances. So SRS is, remember I said how Raman amplification works. So when you use it intentionally, you get a good effect. When it happens unintentionally, what it does is it makes it transfer power from one wavelength to another. And the tighter you pack the channels, the more this occurs. So if you look at, for example, an 80 channel system, and you have them tightly, tightly packing them actually makes it better, which is weird and counterintuitive. But if you take a high channel count system and they're very spread out, then it's very easy for one to transfer power to another. If they're very tightly packed, it's actually better. So you see here kind of the maximum launch power. So if you were running a 50 gigahertz system and you only ran 8 channels, well, you can transmit 21 dBm per channel, which you can't do anyways because of SBS. So you would never see that effect. Whereas if you were down into a very wide space system and you had a very high channel count, you would be very limited, and you usually end up somewhere in that 0-1 kind of range as a transmit out of the gate on most systems. So when you start to go below that, you have to take that into account. So four-wave mixing is what happens when the harmonics of the wavelengths interfere with each other. It's cool how this works. The physics is way above me. But basically, you see you have your 3 good signals here. And what's happened is they've created harmonics. They've created interference that you didn't want, both in themselves and in their neighboring channels. And that's very linked to, if you don't have dispersion, you get these effects very quickly. So here's what's called four-wave mixing efficiency, which is how likely it is to happen. So when you have that point of 0, when you have no dispersion happening on your fiber, you see that it's very, very easy to have very, very thorough mixing until you have very wide channels. And as soon as you add even 1 picosecond per nanometer, you rapidly drop off that mixing efficiency. But then you see 17, the regular SMF, you see that it's dramatically reduced, and you can pack very tight and not see this impact. So here's an example of what that looks like. So if you had a 32 channel system, tightly packed, you see the different limitations, some of which can get very severe, right? If you can't transmit above a -5 or a -6, that's probably going to be a problem in your engineering. The inter-channel effects, XPM and SPM. So cross-phase modulation is what happens when one wavelength of light affects the phase of another. So it doesn't bother So I'll talk about, I probably should reorder this, so I talked about phase earlier, but in an NRZ system, so a very classic brighter dim, we don't care about phase. It doesn't really care. But what happens when you take a old 10 gig NRZ system and you put it on the same line system as a modern coherent system is that 10 gig signal can cross phase modulation in your coherent signal, which does care about phase, and so that's why they tell you don't mix old and new, or if you do, keep them separated with a guard band, specifically for this reason. And once again, high chromatic dispersion actually helps this issue. And then SPM, self-phase modulation, is what happens when the difference between a 0 and a 1 is so strong that it triggers the Kerr effect. And it's weird exotic physics, but if you ever hear the term, there it is. So remember when I was talking about subsea cables and why they were designed for these very wide cores? So if you think about nonlinear effects, this is really an energy density problem. It's what happens when you put too much power in one place at one exact instant. And so ways that you can spread that out, well, one, you can spread out the signal. Two, you can spread it out over time, or three, you can spread it out over space. You can make the core bigger, and so you've spread the power out. So what you do is you get it as close to, you can't go out of single mode, you can't cross into multi-mode, but you can engineer it to have as wide of what's called an effective area. So if you ever want to know what this is, you can go look it up on your fiber specs, and you'll see it listed as the MFD, the mode field diameter, and then you can just pi r squared it, or it'll be listed as effective area. The larger the effective area, the lower the nonlinear effects. So for example, your kind of NZDSF standard is like 50 micron squared effective area. LEAF, which stands for low effect or large effective area fiber, is designed to be a little bit wider. Then you look at your standard SMF, you get all the way up to 80. And then you look at your submarine fiber. So for example, Corning Vascade is a product. You get up into 150 micron squared. So remember, one trade-off here is that the larger the effective area, the less the Raman gain, because Raman is a kind of nonlinear effect. So you trade this off. If you have classic 652, then you get to put more power into the system, but you get less Raman gain. If you have a dispersion shifted fiber, you can put less power in, but you get more Raman gain. So they balance each other out pretty well, but you have to take that into account in your designs. So now I'm going to talk about what we actually transmit over fiber. So remember, at the end of the day, we actually live in an analog world. All these nice ones and zeros have to turn into something that goes out over waves somewhere. And light is just a big electromagnetic wave. So the simplest form of modulation is what's called IMDD. Stands for intensity modulation with direct detection, of which the most common version is something called NRZ, non-return to zero, which is also called amplitude shift keying, ASK, all of which is a fancy way to say bright for a 1 and dim for a 0, right? And that's what most systems have been historically, and that's what everything up into 10 gig absolutely is, up into 40 gig, and even into most 100 gig that's out there as client optics. As you move into newer 100 gig, it's called single lambda 100 gig, as you move into 400 gig, as you move into PAM4, as you move into other things, then we've started to shift away from NRZ into more complicated things. But historically, this is what's out there. So talk about a little bit of background. So baud is what happens when you modulate the signal. You go from a 1 to a 0, and in doing so, you get to say, you go from a bright to a dim, and in doing so, you get to say that was a 1 and that was a 0. And baud is the number of changes per second. So if I plug in a 10 gig LR, what's happening is that thing is flashing brighter dim 10 billion times a second, and I'm decoding that on the other end, and you get 1 bit per baud. So every bright 1, every dim 0, and you see that happen. So that works really well up until a point. So like I said, we historically built a lot of great things until we hit that like 10 gig barrier. And we didn't overcome that until we created, let's see, do I have that in the next slide? I'll talk about that. So where do we go from there, right? Once you start to hit these limitations, how do we keep up with our cat pictures and Russian trolls? Well, what you do is you start to increase the amount of information that you can encode in a single symbol change and a single baud change. So there's two ways to do that. So if you're still in ASK, amplitude shift keying, or amplitude modulation, AM radio. What you do is you have more than two states. So instead of a bright and a dim, you have a bright and a really bright and a dim and a really dim. And the other thing you can do is do phase modulation. So phase modulation, so you've got your analog signal, a nice sine wave, and what you do is both your sender and your receiver agree on a specific frequency. So let's say I'm going to be 192.1000 terahertz, and I agree on the same thing. And the receiver actually has a laser on its receive side, and it dials to exactly the same setting as the other one. So these two things are in sync. They've got the same sine wave, same frequency. And so now the transmitter can just modulate the phase. It can change where that sine wave is, and in doing so, the receiver can detect that and decode it and get information. So that's coherent technology is really when you start to move into using phase shift keying as a part of this. So coherent is really a marketing term-esque that covers a whole bunch of stuff. So it introduces phase shift keying. It's named after so there's a concept in physics called phase coherence. That's what it's named for, but it's the ability to track phase changes in optical. And it's what lets you go, in the early 2000s from that NRZ 10 gig into this new world. Like I said, it has a local oscillator. You dial the local oscillator to match its reference laser, and it's comparing the two. But you have to tie all that together. So it actually requires a lot of really complex DSPs. So you have a digital signal processor. It's basically a little ASIC that's specifically designed for processing analog signals. And a lot of these things are really complex. They're getting up there. They're approaching like CPU level of complexity. There's billions of transistors, there's lots of engineering, and there's lots of science that goes into it. The DSP is what is letting you take all of this stuff and kind of cram it together. But coherent technology also introduced, do I have a slide for that? All right, I'll probably have it coming up. So like I said, you need that DSP to do phase modulation and to tie all the stuff together. The DSP is very expensive, very big, very power hungry, all of that stuff. But coherent is what took us from, we had this hard limit of like 1.6 terabit because we had 160 10 gig channels, and it immediately turned it into, here's 96 100 gig channels, and has gone up 200, 400, 600, 800, and continues to increase. And it delivered true 100 gig optical signals, not just a bunch of N/10s. So then where do you go from there? Right? How do we keep delivering these cat videos? Well, after phase shift keying, then you go to the combination of both phase shift and amplitude modulation, and that's called QAM. So you increase, there's varying levels, and so we've now moved into a world where there's these non-perfectly mapped QAMs, there's dynamically tunable QAMs, there's constellations that adapt to conditions of the fiber. There's all manner of complexity, but let's see, do I have a slide on that? No, I need to add a slide on that. But you computationally increase the complexity of how many bits per baud you can get through more and more complex things, all of which requires better and better conditions on your line system. And so the way it works, it goes into 8 QAM, 16 QAM, 32, 64. So right now, 64 QAM is pretty much the limit of anything practical. And it works great for metro, and it works great for even like, hundreds of kilometers, thousands if you do it right, but not very, very long haul systems. And then very long haul stuff really tends to be 16 QAM or less. So the other thing that coherent technology added was polarization multiplexing. So remember, light is just this electromagnetic wave through space, and you can have a vertical and you can have a horizontal, and the two can co-propagate and not interfere with each other. And so what you can do is, well, hey, that just effectively gave me 2 fibers. So I will split my signal and I'll send one in one polarization, one in the other, but you need that DSP to tie all that together and sort it out. It's something that you wouldn't otherwise be able to do with a kind of a photodiode, bright dim kind of sensor. So how does that all work? Really, the way to think about it is the rate that you get out of your transponder is a combination of polarization times baud times modulation. So polarization right now, there's 2. There's people talking about spin, polarization, and weird things. It's not practical and not going to happen anytime soon. So right now we have two polarizations. You have baud rate. So as your baud rate increases, one thing you have to remember is, and it's the ratio is very close. So if you have a 45 gigabaud signal, you need a 50 gigahertz passband. Something it's very close. So as the baud rate goes up, the size of the channel, the literal width of the channel, needs to go up. You need better and more sophisticated DACs. And then the modulation is the technique that you apply to get more bits per baud. And then as the modulation gets more complex, you need a better quality OSNR, because if you have lower, you can't decode what the signal was intended to be. So here's an example of very basic stuff that is still absolutely out there all over the place, all over the world, 100 gig in what's called DP-QPSK. So you go buy a 100 gig Lambda, and it's not like a new modern system is probably running this. And what this is a 32 gigabaud system with QPSK, which is getting you 2 bits per hertz, and it requires a 37.5 gigahertz system. So that's the stuff that is just, there's tons and tons and tons of it that'll be out in the wild for a very long time. And it will run down to an OSNR of 10, which is, and this is old, by the way. So modern DSPs probably just knock a few dB off of all these numbers. That'll run across the planet and still come out just fine. And then as you want to do more and more stuff, well, okay, how do I get to 200? Well, what I do is I move to, well, I have a choice. I can move to 16 QAM in 32 gigabaud, or I can move to 56 gigabaud in 8 QAM. And they both give me the same amount of bandwidth. One takes a wider channel, and the other requires a higher OSNR. So you have to strike a balance. And the way the modern systems work is they actually give you complete choice. So you have this giant matrix of what you want, and it will, okay, what can I do with the channel conditions that I have? Oh, okay, I can run this thing at 250 gigs. It's very, very flexible. In fact, I think I have a slide from that. Yeah, so this is an example of very popular Acacia AC1200s. This is the DSP that's found in like a whole ton of products that are out there. And you can see the big matrix of what you want to do. So you could say, oh, my line conditions support me using a 48 gigabaud signal, but not wider, and so I can do X with it. It's nice that you get that level of flexibility. You're not baked into your engineering designs when you started. I guess I had this slide on the exact same thing. So yeah, like I said, remember the channel size is increasing proportionally as the baud rate goes up. So that actually matters for a lot of stuff. So for example, a new thing that's coming up that everyone's going to want is 400 gig ZR. Right? There's a talk about it after. Cheap, beautiful, plugs right into your router, it looks great. Some things people don't know about 400 gig ZR. It's a 59 gigabaud signal. It needs a very wide passband mux. Your brownfield muxes will not do it, period, full stop. You need amplification, you need all kinds of other stuff too, but it is becoming more and more the direction that things are going, that we're doing these higher gigabaud signals, and you need new muxes to accommodate that. Coherent. Other big advantages of coherent. It eliminates the need for dispersion compensation completely. It will literally eat 200,000 picoseconds per nanometer and not care, or more. And in fact, it actually works better with coherent, with chromatic dispersion, because the other cool thing is it lets you lock onto a specific frequency. So remember when I talked about contentionless ROADMs, colorless ROADMs, what you could do, you have a splitter, you have like a 32-way splitter, and you just plug in a bunch of transponders. And so now I log into my router and I say, make this channel 1, and I never needed to recable something. I have that level of flexibility because I can exclude through software all of the other channels that I don't want to hear about. But the big downsides of coherent are that it's very expensive and very power hungry. Like I said, it's very, very complex engineering that goes into these things. And the big problem, especially as you talk about how do I get this into my router, is it's big and power hungry and generates a lot of heat and all of that stuff. Historically has been impossible to integrate into pluggables until coming up. So Another thing, I said there's other ways that we can increase the density. What you can do if you stay in amplitude modulation is go from, so NRZ is another way to describe it is PAM2. There's two, it's pulse amplitude modulation, and there's two states. So right, dim 1 0. And this is the eye pattern of what that looks like as the thing crosses and how you're able to detect. So what you can do is move into something called PAM4. So you add 4 states, and then as you cross from, you encode 2 bits per symbol change, and so you walk away. These are the states and what that would map to. So I think probably have a slide on that later. So some more on 400 gig ZR. So this was an attempt to get 400 or get coherent into a pluggable. And the weird thing about this is normally the optical industry and the switching industry don't align. The technology progresses at different rates. And you'll have a new optic technology before the switching technology is ready, or vice versa. If you design a switch that is the most usable in the most places, it's probably not designed for a coherent optic. Now, you could engineer it for a coherent optic, but typically when you do, you create a very small product set that most people don't want. How are we on time? All right. Okay, so 400 gig ZR is actually beautiful because it's one of those rare alignments of the industry. And it's nice because the cost of coherent is, a lot of it is related to scale. So once you do that DSP design, it doesn't cost you that much to keep producing it. So once you've got enough volume going, that's when it really matters. All right, do we want to do questions, or do we want to do a bunch of, where are we at? Okay. Unless anyone has questions, but I'll do this quick. So PAM4 is the underpinning of a lot of new stuff that we're at. So all of your, like I said, all of your 400 gig stuff, all of your 100 gig single lambda stuff, and there's a thing called PAM4 DWDM. And so what they did here is they took 2 28 gigabaud signals, PAM4 encoded, so there's 2 56 gig signals, and they cram them into a single thing. And so now you can deploy a QSA P28 that is tuned, that's not coherent, that you can deploy 100 gig at a time and do these metro distances with. But big caveats, you need these wide passband muxes, you need precise dispersion compensation, you have to amplify 10 dB just to make the things talk to each other, like without even going across the span. There are high OSNR requirements, and you'll never get this thing through a ROADM. But so there's probably not a long shelf life on that technology, but it's for a few years, it's a good cheap way to deploy this kind of thing. And then we're really seeing 400 gigs of ZR because of the volume. It's now getting to a price point that it's highly advantaged. Okay, so now I have a whole bunch of slides on how you do actual optical engineering. So, insertion loss. Remember, even the best splices are not perfect. So every time you connect 2 fibers together, you're going to get loss of some kind. So nice budgetary figure that people use for back of the envelope is like you'll get 0.5 dB just every time you do anything. But it depends on if you've done a fusion splice, if you've got a patch, if it's a clean patch, if Equinix plugged it in wrong, all that fun stuff. So insertion loss is also used to describe the loss that you get anywhere. So if you go through a MUX and you come out 3 dB less, it's the penalty that you get just for plugging the fiber in. We call that the insertion loss. So some real life examples, a common 40 channel AAWG insertion loss will be like 3.5 dB worst case. And then an 80 channel will be 9.5. And you will wonder, why is that? Well, that 80 channel mux is actually 2 40 channel muxes and an interleaver, and that's how you got that number. You will also see bad things if you have mismatched cores, so the fiber sizes don't match. If you have misaligned cores, if you have an air gap between the fibers, if you don't hear a click when you put that that plug in, which happens pretty much everywhere. When you want to do budgetary planning, you have to look at this and say, well, what's going to happen over time, right? What's my fiber loss? What's my splice loss? What happens when somebody goes out and rustles in the cable tray and bends the fiber a little bit? What happens in 5 years when the optic isn't as brand new and shiny and isn't as hot? When an optic says 10 kilometers, this is a guideline only, and sometimes it can be wildly inaccurate. I have literally thousands of optics that are rated for 500 meters that I can put on a 25 kilometer span just fine. Whereas sometimes you'll see something that's rated for 10 kilometers and you will not get 10 kilometers out of it. You really have to do your actual calculations and think about this yourself. The polish connector. So when you look at something, it says LC, and then it'll have a slash PC, UPC, APC, something like that. What that's telling you is the polish of the connector, the interface. So PC and UPC, which actually stands for physical contact, not polish connector, which everyone thinks it does. UPC is just designed to have very low reflections. And then you have something called APC, angled physical contact, that is designed for even lower reflections. So why do you care about that? Well, basically what's happening is the in face is at an angle that's ever so slightly off, so that when you unplug the cable, in a normal system, what happens when you have an open end and you unplug that cable, the power has to go somewhere, it just goes right back. And that can be bad for what you're doing. So in APC, because there's an angle and because you don't have the critical angle for the light to be reflected back, it just goes out into the cladding. So APCs always have these green ends. If you mismatch, if you plug an APC and a UPC together, they will kind of sort of work until they don't. And a lot of people won't know, what's this green cable? I don't know. Because you don't have an exact mating and all of that fun stuff. Reamplifying, reshaping, and retiming. So signal regeneration with repeaters. So this is described as the 3 R's, 1R, 2R, and 3R. So 1R is reamplifying. As you go through an EDFA, you make the signal brighter. Great, it's 100% optical. 2 is reshaping. So you're actually looking at this thing and you're trying to restore some of the original pulse shape, but you're not decoding it. You're not, like, nothing fancy's happening. You're just trying to make the pulse look a little cleaner. And then 3 is retiming. So this is effectively an OEO. This is you literally decode the whole thing back into electrical and then turn it back into optical again and restore it as a perfectly timed, perfectly shaped new signal. I talked about bit error rates earlier. So in optical, things don't go from good to bad. They get progressively worse and worse and worse. And in a basic system, what'll happen is, like, you'll just start having errors and that'll start leading to packet loss, and you, like, might not notice for a little bit until a customer gets angry. In a modern system with FEC, what happens is you can look at the pre-FEC bit error rate. You can actually say, before I fixed it computationally, what was my bit error rate? And you can start to see that this is going to get bad soon. We should do something about it. But when you test a circuit, when you turn up a new circuit and you say, well, I want to know with X amount of confidence that this thing is clean, well, if you want to know, for example, you want to guarantee that a 100 gig link is clean to 10 to the negative 13 bit error rate, you have to transmit at line rate for 3.5 hours. This math. So sometimes, and especially for lower speed signals, when field techs will come out and set up their test gear and leave it running for days, and customers will wonder why. It's because you actually need to leave it running for a very long time to guarantee that your bit error rate is that low. And then here's an example of how OSNR affects different bit error rates. Kind of talked about that in an earlier slide. Tools of the trade, optical power meters. So light meter is literally just a thing that's a photodiode with an output, and it says how bright the signal is. But most light meters come with a relative mode, and you'll frequently see this as dB versus dBm. So dB is expecting a known transmitter on the other side, and you're measuring the loss of the cable. dBm is looking at it and saying, you're putting 4 milliwatts of power into me right now. And so you have to make sure you are in the correct setting. And that's pretty much the cause of almost every data center error when you send the field tech out to go meter a thing and it comes back wrong. It's because they're in the wrong mode. And yeah, I get told that they measured +70 on my fiber all the time, which good luck with that. OTDR. So an OTDR is a optical time domain reflectometer. So what's happening here is you send out a pulse of light and you look for the reflection. You send out a really bright pulse in short bursts. And through looking at how it comes back to you, you can characterize where the splices are, where the loss is. You can do a whole bunch of nice things. And these used to be big, expensive, $10,000 things, and now you can get a thing the size of a pocket calculator that'll do a 60-kilometer span that costs like $500. They're great. They're great in data centers because you can figure out, is the problem in my cabinet? Is it in there? Like, is it in Zayo? Is it in Equinix? It makes life way easier. So here's an example of an OTDR output and what it looks like. So you see the loss, and then you see the places where there's events. And so actually this is an example where you see where it should be a nice steady loss, and then you see it go up and then come back down. That's what's called a grower. So this was an example of a mismatched core type. So this was like above net from 20 years ago, so probably why. But that's an example of what you'll see on an OTDR. But basically you can see, okay, there's a splice 2.3 kilometers away, there's a splice 6 kilometers, there's a splice 10 kilometers, and then you can see what the rate of loss is at each point, and then you can figure out, hey, there's an open cut there, we need to go out there to look for it. So, question people ask all the time, can I really blind myself by looking into the fiber? Or beware, big scary lasers do not look into beam with remaining eye. Which I printed out a whole bunch of these and stuck them on patch panels all over the world, and it freaks techs out. It's great. So laser safety guidelines. Lasers are classified into 4 groups. So class 1, 2, 3, and 4. So class 1 is something that is either completely harmless, either by physics or by like you can't possibly look at it. So for example, your DVD player has a big powerful laser, but it's inside a big metal box that you can't look at, or you look at a laser pointer, you look at a regular optic and says class 1, it won't hurt you. Class 1M is something that is harmless as long as you don't look at it in a microscope. Class 2 is something that is only harmful if you intentionally stare at it. So if you don't want to blind yourself, you go, that's bright, and you look away. But if you do want to blind yourself, you can go, look, Ma, and then you'll hurt yourself. Class 3 is something that should never be viewed directly. So there's an old American system, there's a new international standard. It also breaks down into 3R, 3B. And what's funny is the exact limit depends on the frequency. There's a very complex table that you have to look at to figure out what you're allowed to do. And then as you add these things, you move into requirements like this needs an active safety disconnect. So if it detects a cut in the fiber, it will automatically throttle down. If you need a key to activate it, things like that that are required by law. And then class 4 is something that like burns, melts, or destroys Alderon. So laser safety in the eye. Remember, you're talking about different frequencies, so we actually look at different effects on the body. So IRA, which is called near infrared, is your 850s, your 1310s. That's the stuff that, remember, the human eye is not evolved to look at infrared, so it does a pretty good job of blocking it out. But the closer the signal is to what you normally look at, the easier it is to get through the cornea. And the further away it is, the more your cornea just says no. So the 1550s, the things that you think of as these big high-powered systems, actually do a much better job of not going through your eye. Whereas the things that you don't think of as high-power systems are the ones that actually do. So this is a very, very brief summary of kind of what the power class requirements would be at like 1550, but it's really complicated. There's a big table, and there's a whole document that you can pay $1,000 to get, which I have. So optical safety, routers. Every router that you will ever find, for the most part, is a class 1. If it's a pluggable optic of blah, 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 it's a class 1. It won't hurt you. It's fine. Even the long reach, 200 kilometer, it's not because it's actually a brighter optic. It's because it's more sensitive in its receive. The only time you move into anything that's interesting is when you move into optical amplifiers. So now you're starting to put out power levels that really matter. You're in these like plus 21s. There's like modern PAM4 systems that are like plus 27, which is class 4. Raman is always class 4. Ramans are very bright, so be careful if there's a Raman amp. But these all by law have to have these automatic power shutoffs. But if you're working and you're plugging in your 10 gig or your 100 gig LR, it doesn't matter. The other way that it can matter is if you have DWDM as you mux more channels. So if you take even an unamplified system, but you take 40 channels and you shove them all together in one fiber, you've now got a very bright fiber. And even what people don't think about is like an LR4 is 4 lasers that are muxed together. So that's 6 dB brighter than what would normally be under normal conditions. So, but for the most part, it's just never a thing that you have to worry about if you're out plugging in basic stuff. So should I be wearing safety goggles in the colo? No, but be aware of what you're working on, and don't for the most part, if you don't hold the fiber to your eye, you're fine. And also be careful with making sure nothing is lit when you plug in with a microscope. So why would you even look into fiber anyways? Can you see it? Well, technically speaking, no telecom signal is directly visible to the human eye. But if you say, hey, I plugged in my 850 and I saw red, what you're seeing is a sideband. It's not precise, and you're seeing a little bit of red. Most of it is in infrared. But a cool trick that I used to use, but they fixed these in all the new phones, but you used to be able to take your camera phone out and plug it up and it would see IR very well. But as they try to make the picture quality better, they start putting more filters on the glass, but you can see the IR that way. So people ask, can optical transmitters be damaged by can you damage a thing with an overpowered transmitter? And like I said, yes and no. So when you talk about a long reach optic, what happens is in order to get longer and longer reach, you're more and more sensitive. And so that if you take an 80-kilometer optic, you take 2 of them back to back, yes. And there's what's called a saturation point and a damage point. So this is like probably a 15-year-old slide from 10 gigs or something, but you can see that in LR, it's completely impossible. Even if you take a full power transmitter and plug it in right into a receiver, you're way outside of anything. In a 40-kilometer optic, you can move into a point of saturation. You can move into a point where it doesn't work, but not damage. And then in a long reach ZR kind of optic, you can absolutely damage the optic. People ask, do I need to be concerned about bend radius? Yes, it's a real issue. And in fact, if you want to, the way that you find weird loose fibers is you plug a red light on the end and you go out and you bend the fiber and you see it, just like that. As you bend it past its critical angle, it makes the light leak out. Critical bend radius, something, probably need to talk about that. Can 2 transceivers of it? So cool thing that a lot of people don't understand is the optics don't actually have to be the same frequency to talk to each other. Coherent they do, because that's how coherent works, but everything else, you can take a 1310 and make it talk to a 1550 and it works just fine. DWDM systems that are built on single strand use this. The only gotcha about the whole thing is it'll make your optical power meaning wrong. So if you expect a 1310, you get a 1550, you'll be off by a couple dB, so you have to make sure your mode is set right. But it's a cool trick to let you do weird things. So like if you only have one LR and one ER optic, you can get 30 kilometers of reach because the one side is more sensitive and the other side is more power, and it balances out. Do I really need to clean the fiber? Yes, you do. If you think about the mating force of 2.2 pounds over a 200 micron area, it's 45,000 pounds per square inch of pressure. So if you have a tiny little piece of dust in there and these things come together, it will literally chip the end of the connector and it will just permanently damage it. Other miscellaneous fiber information, how fast is light travel in fiber? So you can do the math on this and you can see that 1 millisecond of propagation time is 200 kilometers, or cut that in half for round trip time that you see in a tracer out. So when the fiber goes 100 kilometers, it has added 1 millisecond of latency. And if you go, why is my latency much higher than that? Remember, fiber is never laid in straight lines. It's probably going in weird loops and has lots of spools and things like that. But that's the basic distance calculation on it. And that is about it, with a few minutes for questions.
Well, thank you, Richard. We do have some questions from the virtual audience. We'll take one from the virtual audience first and then from the in-person. First question is from Adair Daxton. How did they figure out the dispersion correction stuff? Who was the first to say, hey, just leave a big spool of fiber and see what happens?
I don't know who specifically, but The thing, if you look at historically, what happens is some scientist in a lab somewhere created a thing probably 40, 50 years before it became used in the industry. And it only existed in a very specific lab in very specific conditions. And then they go, okay, what can we do with that? And someone will eventually create it. So they knew a lot about the chemical engineering of the composition of the fiber, the atoms, how it worked, why it worked, what that light looked like 40, 50 years before. And when you actually go to build a system, they refer to that engineering to figure out how to make it work.
Awesome. Please state your name and your affiliation.
Hi, Alex Latsko, netbusters.com. Actually, kind of interesting question. You gave us the speed for fiber, but I noticed that there's different speed between fiber and copper in long hauls. Can you tell us what the difference is?
Different speed between fiber and copper?
Yes.
So when light is propagating through glass, it's transmitting at like 0.67 C, so 2/3 the speed of light. When electrical signals are moving through RF, copper, there's different propagation. So people do, like, that's why low latency, high frequency stuff is done with microwaves, because it transmits faster. That's why SpaceX is creating a low latency product with lasers between birds, because it's actually lower latency to send it up and go through free space laser than it is to go through fiber. And then you get into all kinds of shenanigans like hollow core fiber. We could talk about that for hours.
Thank you.
Thank you. Moving on to the second question from the online audience, from Tony Tauber. It's always seemed to me that the economics of wavelength on demand setups aren't compelling. Example, deploy a bunch of expensive gear just in case the demand shows up. Am I missing something?
Yeah, welcome to telco. It depends, right? So if demand shows up and you can charge a bunch of money for it, then sure. But yes, the industry is obviously littered with bad investments and things that are spent. It is very much a trade-off between if you're trying to build an optical transport network where you can deliver any service between any point for any customer. You're an AT&T, you're Verizon, you build in a very specific way. When you are a Google and a Facebook and you're trying to build for high efficiency transport to support a packet network or something else, you build in a radically different way. So I personally live more in the low price per bit world, and so I try to avoid ROADMs, and I try to avoid things that will destroy my OSNR, and I try to avoid all of that dynamic tunability stuff. But there's absolutely a benefit for it if you live in the other world.
Perfect. Please state your name and affiliation.
Hey, hi, I'm Brian Fields. I'm with Nokia. I actually have one thing. It's kind of a comment, and it says don't give comments, but something I've used that kind of separates the pros from the hacks before, like for interviews. I asked somebody, what's 0 dBm plus 0 dBm? You don't have to answer that. It's just, it's a thinking question. My actual question is, and this was early in your talk, you said multimode fiber is more expensive. I'm wondering why that is. Is it just economies of scale, or why?
Good question. Not sure. I mean, it's not appreciably more expensive, but it's like 50% more expensive. I mean, it would add up if you did a lot of multimode. But you'll see this where you're like, oh, I've got a $100 optic that needs 8 lanes of multimode in a data center. Well, you went from using a $2 cable to using a $30 cable because you've added more strands and moved into multimode.
Okay, thanks.
And labor.
One more question from the live audience. Is hollow fiber a real usable technology today? Will it be in the future with less .NET?
Interesting question. So I'm told by the people that know that it is a thing that people use. But if you think about it for HFTs, right, where they're out optimizing nanoseconds. If you think about it in a practical sense, what's the likelihood you're going to be able to splice fiber that you need to maintain a vacuum on? Right? This is not going to be a thing that you're going to run across in the real world. But if you're a very, very, very specific customer doing very specific things, yeah.
Great. Please state your name and affiliation.
Hi, I'm Barry Cook, and I do contract work for Fastmetrics and Atherton Fiber. And I was wondering if you had any more information on 1x32 splitters and the loss you incur, and also bidirectional fiber as it relates to that?
Bidirect. So the loss on the splitter is exactly what you would expect. So if you split a 1x2, it's a 3 dB loss plus a little bit of overhead, right? So the technology that is mostly used for that is what's called a PLC splitter. So I forget what a 30 is, like 20 dB or something. I forget off the top of my head, but it's very cheap. It's very common. It's very commonly used for those distribution systems. But what do you mean the bidirectional?
For fiber to the home, I've seen some bidirectional fiber in use, so you don't have to send 2 fibers to each house. So with an attenuator, it's hard to know which which direction is supposed to be attenuated. I guess that's my question.
Yeah, so when you go through the splitter, and it's weird, right? So if you think, well, I took the signal and I split it 32 ways, so I get 1/32 of my signal, but I'm going the other way. I'm transmitting this thing. What's my loss? It's the exact same. You will get the same loss going in because it's
okay.
It doesn't, that's how it works. So you'll get much less loss if you just use a mux at that point, but that might be more expensive than a splitter. So if you're doing fiber to the home, you're using fiber in a very different way than a data center. It's a glorified cable at that point. Even though it's fiber, it's used more like a cable modem than a 10 gig pluggable.
More for like GPON or something.
Yeah.
Thanks.
Well, I think we're out of time.
All right.
Thank you, Richard. We really appreciate your time today.
Thank you.